Department of General Engineering from Emmanuel J.J. College of Engineering, Natala. I am going to teach the topic two-dimensional random variable. First, I explained the definitions. First, let S be the sample space. Let capital X equal to X of S and Y equal to Y of S be two functions, each assigning a real number to each outcome. Small s belongs to capital S. The capital S is the sample space. The sample space comes from the population. Then the random variable x comma y is a two-dimensional random variable. If the possible values of x comma y are finite or countably infinite, then x comma y is called a two-dimensional random variable. The random variable x comma y takes a particular values. For example, x equal to 0, 1, 2, 3 here. Then we say x comma y is a discrete random variable. Otherwise, x comma y take a period, that is for example 0 to 3 or 0 to 5 or 0 to infinity. Then we say the random variable x comma y is continuous random variable. If x comma y can assume all values in a specified region or in the xy plane is called a two-dimensional random variable. Discrete random variable. The joint probability distribution is defined by capital F x comma y of x comma y equal to probability of x comma y, that is capital X less than or equal to small x, capital Y less than or equal to small y. The joint probability function or the joint probability mass function of the discrete random variables x and y, provided the following conditions are satisfied. First condition is the probability is greater than or equal to 0 for all the values of I and j. The second condition is summation j summation I p I j equal to 1. That means the total probability equal to 1. Next, the marginal distribution of x is given by small f of x equal to p capital X of x equal to pi. Similarly, the marginal probability mass function of y is given by f of y equal to pj. The conditional probability of x given y is f of x given y equal to f of x comma y divided by f of y. Similarly, the conditional probability density function of y given x is f of y given x equal to f of x comma y divided by f of x. Only one difference, x given y means in the denominator we are having f of y, y given x means if the denominator having f of x. Two random variables x and y are said to be independent if pij equal to pi into pj. The product is equal to the probability, then we say the two random variables are independent, otherwise we say dependent. Then continuous random variable. The joint probability density function of the continuous random variable x and y, provided the following conditions are satisfied. For continuous random variable, f of x comma y is always positive. Double integral f of x comma y dx dy equal to 1. Same meaning, the total probability equal to 1. Then the marginal density function of x is f of x equal to integral f of x comma y dy. That is denoted by f of capital X of small x. Similarly, the marginal density function of y is f of y equal to integral f of x comma y dx. That is denoted by f capital Y of y out. That is, the marginal density function of x is the integration with respect to y. Understand the difference. The marginal density function y is integrate with respect to the x. For x, integrate with respect to y. For y, integrate with respect to x. But the limit is same, minus infinity to plus infinity. The integrand also for two formulas f. So, f of x equal to f into dy, f of y equal to f into dx. If x comma y is two-dimensional continuous random variable, then capital F of x comma y is probability of capital X and capital Y is called the cumulative distribution function of x comma y and is defined by capital X comma y equal to double integral small f dx dy. Let x comma y be two-dimensional random variable and capital X the joint probability distribution function, then the joint probability density function is defined by capital F equal to dou square of capital F divided by dou x dou y. Now we are going to the problems. The first problem is in discrete random variable. Given the function is p of x comma y equal to k into 2x plus 3y. X varies from 0 comma 1 comma 2 and y varies from 1 to 3. That is, the x takes the particular values 0, 1 and 2. Similarly, y also takes the particular values 1, 2, 3. So, the given problem is under discrete random variable. The question is, find all the marginal conditional probability, also probability distribution function of x plus y and probability function of x plus y greater than 3. In this question, given p of x comma y or f of x comma y, p of x comma y equal to k into 2x plus 3y. X takes 0, 1, 2. Similarly, y takes 1, 2, 3. That is the given question. From this question, we find marginal distribution of x, marginal distribution of y, conditional probability of x given y, y given x, then probability distribution function of x plus y and probability of x plus y greater than 3. These are the questions. First, the given PDF has one constant k. So, first we eliminate the constant. Eliminate the constant. How to eliminate the constant? We have one property. Total probability equal to 1. Total probability equal to 1. Using that condition, we find the constant value. First you put the tabular column. X value is 0, 1, 2. Y value is 1, 2, 3. Given f p of x comma y equal to k into 2x plus 3y. So, for the first cell, listen all of you, x equal to 0, y equal to 1. So, in the PDF, you put x in the place of x 0, in the place of y 1. That is, we replace x by 0 and y by 1. Then we get 2 into 0, 0, plus 3 into 1, 3. So, now we are having one constant, k is an outside, so 3 into k. Similarly, we find all the values in the cell. Second cell, x equal to 1, y equal to 1. Next, x equal to 2, y equal to 1. Second row, x equal to 0, y equal to 2. X equal to 1, y equal to 2. X equal to 2, y equal to 2. Third row, x equal to 0, y equal to 3. X equal to 1, y equal to 3. X equal to 2, y equal to 3. In this way, we can find all the cell values. Then the probability. Just you find the sum of the first row. Sum of the first row. 3k, 5k, 7k. What is the sum? 3 plus 5, 8. 8 plus 7, 15. So, we are having one constant k, so 15k. Similarly, 6k plus 8k plus 10k, that is 24k. Similarly, 9 plus 11 plus 13, 33k. In this way, we find the sum of columns also. Sum of column. First column, 3 plus 6 plus 9, 18. Similarly, 5 plus 8 plus 11, 24. 7 plus 10 plus 13, 30. Then we check the sum of the probability column. Similarly, the sum of the probability row, that should be equal. Otherwise, we put any mistake. Here we are getting 72k. Balancing. row and column are values. That is the total probability. We have the property total probability equal to 1. So we write 72k equal to 1. From this we find k equal to 1 by 72. Isn't it? Okay. Next, the next question. First we eliminate the constant. For every questions we are having constant. First we eliminate the constant using the condition the total probability equal to 1. Okay. Next we are going to the marginal distribution. From the table directly we write the marginal distribution. What is the first cell? P. First marginal distribution of x. Okay. What are the values of x? 0, 1, 2. Where x equal to 0? Here x equal to 0. That is equal to x equal to 0. The probability equal to 18k. Directly you write 18k. Next you replace k by 1 by 72. In the place of k you write 1 by 72. Isn't it? So we are getting P of x equal to 0 equal to 18k equal to 18 by 72. Next value 1. So P of x equal to 1 equal to 24k. 24k equal to 24 into 1 by 72, that is 24 by 72. Similarly, P of x equal to 2. P of x equal to 2 equal to 30k. That is 30 into 1 by 72, that is 30 divided by 72. Similarly, we can write the marginal distribution of y. First y value is 1. So P of y equal to 1 equal to 15k. That is 15 into 1 by 72 equal to 15 by 72. Next value P of y equal to 2. P of y equal to 2 equal to 24k. 24 into 1 by 72 equal to 24 by 72. Next value P of y equal to 3. P of y equal to 3 equal to 33k. 33k equal to 33 into 1 by 72, that is equal to 30.